Welcome back to Mechanical Engineering Made Simple. Today we are going to talk about a device that arguably breaks the rules of how we think engines should work.
That's a bold start. Usually when we talk about engines on this show, we're talking about, fire, pressure, noise, all sorts of moving parts.
Exactly. But today we are talking about a magic box. Just bear with me on the metaphor for a second.
Huh.
Imagine a box where you feed fuel in one side, let's say hydrogen, but instead of exploding it,
Right.
instead of pistons slamming up and down or turbines spinning at 10,000 RPM, this box just sits there, silent, stationary.
Hmm.
And yet out the other side comes pure electricity and a little bit of water.
You're describing the fuel cell. And, while I cringe a little at the word magic, you're right that compared to the violence of internal combustion engine, a fuel cell feels impossibly clean.
It does.
But as our source material for this deep dive reminds us, it isn't magic. It's thermodynamics. Specifically, it's a masterclass in how to, cheat the limitations of the steam age.
And that is the mission for this deep dive. We're walking through a classic text on engineering thermodynamics, specifically the chapter dedicated to fuel cells. We're going to answer the questions that usually stump people online.
The big ones.
Yeah, like, why are steam engines and gas engines fundamentally imperfect? How do you actually get energy out of fuel without setting it on fire? And the big one. What are the physics limits of a battery that never, ever runs out?
It's a fascinating area because it really bridges the gap between two worlds that engineers usually keep separate.
What's that?
The mechanical world of heat engines and the chemical world of batteries. Our source takes us all the way from the 1880s when scientists first realized we were converting energy all wrong, right down to the complex math of electrochemical potential.
So let's start with the why. We've been building steam engines and internal combustion engines for over a century. They power the entire world. Why are we trying to fix what isn't broken?
Well, the source argues that they are broken, or at least they're fundamentally flawed. The text refers to them as cyclic devices. Whether it's a massive steam turbine in a power plant or, the V6 in your car, the process is the same. You take high-quality chemical energy, the fuel, you degrade it into heat,
By setting it on fire.
and then you try to convert that disordered heat back into organized work, into motion.
And that middle step, the heat, that's where the problem is, right?
Precisely. The second you turn energy into heat, you're subject to the second law of thermodynamics. You are handcuffed by the Carnot efficiency limit.
The Carnot limit. That's the rule that says you can't just use all the heat. You have to throw some of it away.
You have to pay a tax to the universe.
Yeah.
To make a heat engine cycle actually work, you must dump a significant portion of that heat into a cold sink.
Like a cooling tower or your car's radiator.
Exactly. You literally cannot convert 100% of heat into work. It's just physically impossible.
And that tax is expensive.
It is huge. The source notes that even our most sophisticated rotating machinery, the absolute best turbines engineering can produce, are practically limited to about 50% efficiency.
50%.
So for every unit of fuel you buy, half of it is just warming up the atmosphere.
That brings us to the historical pivot in the text. Who was the first person to look at a steam engine, see that 50% loss, and say, this is garbage?
That would be Wilhelm Ostwald, way back in 1880.
No way.
Yeah. He was looking at the steam engine, and he wrote, and I love this quote because it's so understated, he called it an imperfect thing.
Imperfect. That is a very polite way of saying incredibly wasteful.
It is. Ostwald had this realization. He looked at galvanic cells.
What we call batteries today.
Like batteries. And he realized they weren't heat engines. They don't burn fuel to make heat. They convert chemical energy directly into electricity.
Because they skip the fire step.
They skip the fire step, and because they do that, they skip the Carnot limit. They don't have to pay that massive heat tax.
So if we just strip away those heat engine limitations, what kind of efficiency numbers are we talking about? If a gas engine is stuck at 50%, what's the ceiling for a fuel cell?
The source cites conversion efficiencies for chemical processes in fuel cells as high as 60% to 80%.
That's a massive leap.
It is, but there's a nuance here that's even more important for anyone who drives a car.
What's that?
Think about a standard engine. It's most efficient when it's running hard, right? High speed, steady load.
Okay.
But if you're stuck in traffic, idling, or just creeping along, your efficiency tanks. You're just burning fuel to keep the engine spinning.
Right. Part load efficiency is usually terrible for combustion.
Exactly. But a fuel cell, its efficiency isn't really reduced by part load operation. In fact, the source points out that it often runs better and more efficiently when you aren't demanding maximum power.
That's a complete game changer for, say, urban transportation where you're always stopping and starting.
A total game changer.
Okay, so we've established the motivation. Burning things is inefficient. We want to do what a battery does, direct conversion. But to understand the fuel cell, the source actually takes a step back to the ancestor of all this, the Daniel cell.
Right. You can't really understand the complex version without the simple one. The Daniel cell it's the classic blueprint of an electric cell.
So paint the picture for us. What does this thing look like?
Imagine a vessel. Inside, you have two different liquid solutions, and they're separated by some kind of boundary, maybe a porous pot or a membrane.
Okay.
On one side, you have a solid zinc electrode sitting in a bath of zinc sulfate. On the other, a copper electrode and copper sulfate.
Zinc on the left, copper on the right. Simple enough.
Now, if you just threw a piece of zinc into copper sulfate, it would react, get hot.
A chemical reaction, like a mini combustion.
Exactly. But here, we separate them. The zinc dissolves into the solution. And when a zinc atom leaves the metal bar and enters the liquid, it leaves behind 2 electrons.
And those electrons are now just stranded on the zinc bar. They want to get to the copper side, but they can't swim through the liquid.
Correct. The liquid blocks them. So if you connect a wire from the zinc to the copper, the electrons finally have a path.
And they rush through it.
They rush through that wire, that flow, that is your electricity. They travel over to the copper side, where copper ions in the solution grab them and turn into solid copper plating on the electrode.
So it's a cold burn. You're getting the energy of the reaction, but instead of heat, you get work moving through the wire.
That is the perfect way to visualize it. The source explains this using the first law of thermodynamics. In an open circuit, you have this chemical energy just waiting to be released. We call that the Gibbs energy.
And there's some specific math the source uses to calculate exactly how much power we get, right? It's not just a guess.
Oh, it's very precise. The text uses Faraday's laws of electrolysis. It establishes a clear relationship between the amount of stuff reacting and the electricity you get out.
Walk us through that equation. I see it here. Delta W equals Z times F times E. What are we looking at?
It's simpler than it looks. Delta W is the electrical energy you get. Z is the valency. That's just how many electrons an atom gives up.
For zinc, that would be 2.
2, F is Faraday's constant. You can think of that as the total electric charge in a big bucket of electrons, a mole of them. And E is the voltage.
So work is the number of electrons times the charge of those electrons times the voltage that's pushing them.
Spot on. And for this specific Daniel cell, at about 25 degrees Celsius, the text gives the electromotive force, the EMF, as roughly 1.107 volts.
1.1 volts. So it's small. It's essentially a AA battery.
Okay, much.
But it proves the concept, direct conversion. However, there is a problem with the Daniel cell, and really with all batteries. They die.
The zinc eventually dissolves completely. The fuel is trapped inside the casing. Once it's gone, the party is over.
And that is the transition to the fuel cell. I think a lot of people get confused here. Is a fuel cell just a fancy battery?
Structurally, yes. Functionally, no. A battery is a storage device. It contains all its fuel inside. A fuel cell is an engine. It's an electric cell where the electrodes, the fuel, are continuously supplied from the outside.
So it's a battery that never dies as long as you keep feeding it?
Precisely. Let's look at the hydrogen-oxygen fuel cell. That's the standard model discussed in the source.
How is the setup different from the zinc and copper one? We aren't dissolving metal bars anymore.
No. Here, the electrodes usually made of platinum. They aren't the fuel, they're just the stage where the action happens. The platinum acts as a catalyst.
Okay.
You pump hydrogen gas to the anode, the negative side, and oxygen to the cathode.
And the electrolyte in the middle?
It could be a few things, but the source describes using something like dilute hydrochloric acid or potassium hydroxide. The magic happens right at the surface of that platinum.
How does it work?
Hydrogen flows in, hits the platinum, and the bond breaks. The protons, the H+ ions, they swim through the liquid. But the electrons,
They get forced to take the long way around, through the wire.
powering your motor, your lights, whatever you have connected. Then they meet up with the oxygen and the protons on the other side.
And the only thing coming out the tailpipe is water.
Just water, H2O. It's remarkably elegant. Hydrogen plus oxygen equals water plus electricity.
Now, the source actually throws a curveball here. It shows a diagram of a proposal for a vehicle.
Yeah.
But it doesn't carry hydrogen tanks. It carries methanol. why complicate things with methanol?
This is a nod to the real-world logistics of engineering. Hydrogen gas is, well, it's fluffy. It's low density. Even when you compress it, it takes up a lot of space. Methanol is a liquid at room temperature. It's easy to pump, easy to store.
And we already have gas stations designed for liquids.
Exactly.
But you can't just feed methanol directly into a hydrogen fuel cell, can you?
No, not directly. So the vehicle uses a chemical trick called the water-gas reaction. The car basically has a device called a reformer on board. It takes the liquid methanol, reacts it with water, and it cracks it open to release the hydrogen gas right there on the spot, just before it enters the fuel cell.
That's very clever. It's like carrying a dehydrated meal and adding water right when you want to eat instead of carrying a heavy soup around all day.
It's a bridge technology. The text mentions that while commercial fuel cells are still maturing, we've seen them in spacecraft and some large-scale applications, like a 1-megawatt plant built by Tokyo Gas in Japan.
Okay, so we've covered the what and the how. Now I want to get into the physics, because I think the most common misconception is that this electricity just happens. But there's a force pushing these electrons.
Right, it's not magic. It's something the text calls electrochemical potential.
The source uses a symbol for this, a Greek mu with a little tilde over it. It looks complicated, but what does it actually represent?
Think of it as chemical pressure combined with electrical pressure.
Okay.
Chemical potential is the desire of the chemicals to react like a rock wanting to roll downhill. Electrical potential is the attraction of the positive and negative charges. Electrochemical potential combines those two into one single value that tells you how badly the system wants to reach equilibrium.
And equilibrium means the battery is dead. So we want to stay as far away from equilibrium as possible to get power.
Exactly. As long as there's a difference in this potential between the anode and the cathode, current will flow. The source introduces the Nernst equation to quantify all this.
And this relates back to that Gibbs function we mentioned earlier.
Right. The maximum electrical work you can possibly get is determined by the change in the Gibbs function, delta G. And the critical rule to remember from the text is this. If delta G is negative, the reaction is spontaneous.
It wants to happen. It produces power.
Yes. And the Nernst equation links that chemical desire to the voltage you actually see on the meter.
So the standard EMF, E0, is derived from that Gibbs energy.
It is. It's basically, here's the total chemical energy available, divided by the number of electrons, gives you the voltage per electron. It's a direct conversion.
Now, here's where the thermodynamics gets really counterintuitive for me. I think most people assume that if you want a chemical reaction to go faster or work better, you heat it up.
Sure, fire burns hotter, engines run better when they're warm.
Exactly. But the text raises the question, does it work better if it's hotter? And the answer is no.
In this specific case, surprisingly, no. You have to look at the type of reaction. The hydrogen-oxygen reaction is exothermic.
Meaning it releases heat as a byproduct.
It gives off heat. Right. Now, there's a principle in chemistry, Le Chatelier's principle, that basically says if you add more of what a reaction produces, you actually choke the reaction. Since the reaction already produces heat, if you add more external heat, you're fighting against the process.
That is fascinating. So a hotter fuel cell theoretically produces less voltage.
The source references the Van Hoff equation to prove this. It shows that as temperature, T, goes up, the EMF, the voltage, actually goes down. It's a fascinating balance because in practice, engineers might need some heat to keep the catalyst happy or to keep the water from freezing, but thermodynamically, heat is the enemy of voltage here.
What about pressure? In a piston engine, compression is everything. If I squeeze the gas in a fuel cell, does that help?
Yes, pressure helps. The source gives a specific calculation for this. If you raise the pressure from 40 bar to 80 bar, so you double the pressure, the voltage does increase.
By a lot.
Not really. The calculation shows an increase of about 0.0075 volts.
That seems negligible.
It's small per cell. But if you have a stack of hundreds of these cells, it starts to add up. Still, the takeaway is that the chemical drive, the bond energy, is much, much stronger than the mechanical pressure drive. You can't just squeeze more power out of it easily.
So let's look at the balance sheet. We have this silent engine. It bypasses the Carnot limit. It has no explosions. Why isn't it 100% efficient? The source mentions an efficiency paradox.
This is the so what of the physics. Even though it's not a heat engine, the fuel cell cannot escape the laws of entropy.
Entropy, the measure of disorder in the universe.
Right. Think about the reactants. You have hydrogen gas and oxygen gas. They're chaotic, flying around, bouncing off walls. That's high entropy.
Okay.
When you combine them into liquid water, you're constraining them. You're creating order.
And nature doesn't like it when you create order for free.
Exactly. You have to pay for it. To pay for that creation of order, the system must dump energy. The term in the equation is T times delta S. Because the entropy change is negative, we're becoming more ordered, the cell must give off some heat to the surroundings just to stay at a constant temperature.
So that heat is lost energy. It's not friction, it's not bad design, it's just physics.
It's fundamental. It's energy that cannot be turned into electricity because it must be paid to the universe to satisfy that entropy change. The source calculates that for a hydrogen-oxygen cell at 25 degrees Celsius, this entropy penalty reduces the theoretical maximum efficiency to about 94.5%.
Still, 94.5% is incredible compared to the 50% of a steam turbine.
It is, but that is the theoretical limit. The source then drags us back to reality with a section on irreversible thermodynamics. Because, as we know, theory is nice.
But reality is messy.
Very messy.
Right. Nothing is perfect. What slows us down in the real world?
The text lists a few big losses. First, ohmic losses. The electrolyte itself has resistance. Just like a wire heats up, the liquid heats up as ions move through it. That's lost voltage.
It's basically chemical friction.
You could call it that. Then you have concentration gradients. Imagine the ions trying to get to the electrode. If you demand a lot of current, if you floor the gas pedal, the ions start to crowd up at the electrode. They just can't diffuse fast enough. We call that polarization.
So as you ask for more power, more current, the actual voltage drops.
Yes. The source defines this with current density, J. As J increases, the voltage drops further and further away from that perfect 1.1 or 1.2 volts.
It sounds like a traffic jam.
That is a perfect analogy. At low traffic, everyone moves at the speed limit. That's maximum voltage. But as you pack more cars, more current onto the road, everything slows down, congestion builds, and you lose potential. You lose efficiency.
It's interesting because this brings us full circle back to that magic box idea. We want it to be infinite power, but it's still subject to resistance and crowding.
Exactly. But even with those real-world losses, it operates on a completely different plane than the combustion engine.
So let's zoom out and look at the big picture here. We started with the steam engine, a loud, hot, messy device that relies on the chaos of fire and throws away half its fuel just to follow the rules.
And we ended up with the fuel cell, a device that is all about control.
It really is a different philosophy of energy, isn't it?
Completely. The steam engine tries to harness chaos. It creates a fire, pure chaos, and then tries to force it into mechanical motion. The fuel cell is about precision. It takes the chemical bond energy and it guides the electrons specifically where we want it to go.
It's interesting that the source reinforces that while fuel cells are constrained by the first law, you can't create energy, they dodge that heavy tax of the second law that limits all combustion engines.
They do. They are the closest we get to pure energy conversion. We aren't limited by the temperature of the fire or the coldness of the radiator. We're only limited by the chemistry itself and the speed at which we can move ions through a fluid.
It really makes you rethink how we use energy. We usually burn hydrogen to get heat, accepting all that chaotic waste of energy. The fuel cell asks, what if we simply guided the electrons to their destination instead?
It's a fundamental shift from brute force to precision. And in engineering, precision usually wins in the long run.
That is a fantastic thought to end on. From the clunky steam engines of 1880 to the electrochemical potential of the future, it's all about finding a better way to move energy.
And understanding the thermodynamics behind it all.
Absolutely. Well, that wraps up our deep dive into the silent engine. If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.